This video looks at the concept of independent events. Two events are independent if the occurrence of one does not influence the occurrence of the other. So take for example, we have a case where we have event A and event B, and we're given that the probability of event A is equal to 0.6. And we're also given that the probability of event B occurring is equal to 0.4. Now, if event A and B are mutually exclusive, so I'm going back to the topic of the previous video. If event A and event B are mutually exclusive, the probability of event A, given that event B has occurred, is going to be equal to 0. The probability of A occurring is 0.6, but once you're told that event B has occurred, the probability of A becomes 0. Now, if the event, so I'm just going to put MUT just to signify mutual exclusiveness. Now, if you're told that events A and B are independent events, that means the occurrence of one event does not influence the occurrence of the other. That means that the probability of event A, given that event B has occurred, is still the same 0.6. What am I saying? I'm saying that the information that B has occurred does not have an influence on the probability of A. Hence why the probability of A, given that event B has occurred, is the same thing as the probability of A. And that's what this equation says here. It says if two events A and B are independent, the probability of event A, given that event B has occurred, is equal to probability of event A. The probability of event A isn't changed due to the occurrence of event B. So here's a definition. It says that the probability of event A given event B is equal to the probability of event A and B occurring divided by the probability of event B occurring. Now, this is just a definition. It's actually come from an area of maths known as conditional probability, which is not in the WIC syllabus, but I'm going to use this expression to get to something that is actually in your syllabus. Now, if you just accept that this equation is true, so let me just stress that this means probability of A and B occurring. So we're saying the probability of two events occurring. For instance, saying the probability that James buys milk and James buys water, something like that. That's what this means. If you don't set theory, you know about intersections. You can have this as an event, for instance, and this is another event. Their intersection is what's represented by this expression here. But that's not our main focus here. If you accept this expression, if event A and B are independent events, then it means that this term here, probability of A given the probability of B, is equal to the probability of A. Knowing that event B has occurred does not influence the probability of A. That means I can replace this, which is this here, I can replace it with this. And doing that gives the following: probability of A is equal to probability of A intersect B, or the probability of A and B occurring divided by the probability of B. Now if I cross multiply, so probability of A is same thing as probability of A over 1, same thing. Any fraction, 2 is the same thing as 2 over 1. That's just the same principle I'm applying here. Now if I cross multiply, I get the following: the probability of A times the probability of B is equal to the probability of A and B times 1, which is the same thing as probability of A and B. And this I can rewrite as this: the probability of A and B is equal to the probability of A times the probability of B. That's what we get from here. Probability of A times probability of B is equal to probability of A and B occurring. So let me just swap the left hand side with the right hand side to give this expression. So this expression here applies to independent events. And what this is saying is the probability of an event and another event occurring is equal to the product of their probabilities. So the probability of event A and event B occurring is equal to the probability of event A times the probability of event B. So this is an equation you need to remember, and it applies for independent events. And while we're here, let's look at the case for mutually exclusive events. Now, if I ask you what the probability of event A, I'll just put a prime here, and event B, when A prime and B prime are mutually exclusive, so A prime and B prime are mutually exclusive, what's the probability of event A prime and B prime occurring? That's simply equal to 0, because you know once one event occurs, the other event will not occur. So the probability of two mutually exclusive events occurring is obviously 0. It's impossible because once one occurs, the other can't occur. So all our focus is now is just on the probabilities of two independent events occurring. What if we had three independent events? The probability of event A and event B and event C. That's simply going to be equal to the probability of event A times the probability of event B times the probability of event C. So you get the idea. If you had 4 events, the probability of those 4 events occurring is the product of the probabilities of the 4 events. So you get the idea. But this is all you have to remember. You can also write this down. You probably won't have cases with more than 3 events when you're applying this equation or formula. So say event A and event B are independent events. We just looked at the probability of both the independent events occurring. We look at the probability of event A and event B occurring. But now we're going to look at the probability of event A or B occurring. And that's given by this formula. The probability of event A or B occurring is equal to the probability of A plus the probability of B minus the probability of A and B. Now just taking a step back, when we looked at mutually exclusive events, we looked at the probability of A or B. So I'm going to call this A prime and B prime. So A prime and B prime are mutually exclusive events. The probability of A prime or B prime occurring is we found that is equal to the sum of their probabilities. But this formula comes from here because if I write this expression in this form, I'll have the probability of the first event plus the probability of the second event minus the probability of both events occurring. Now, A prime and B prime are mutually exclusive events. So the probability of both events occurring is obviously 0 because they're mutually exclusive. Both of them can't occur. So this is simply so events A prime and B prime are mutually exclusive. The probability of A prime or B prime occurring is equal to the sum of their probabilities. But it comes from this equation, which is the same equation here. For independent events, the probability of the two events occurring is not 0. So you have to include it in the equation. So you just have to remember this. The probability of A or B occurring is equal to the probability of A plus the probability of B minus the probability of A intersect B, or the probability of A and B occurring. And I'm just going to use set theory to demonstrate why this formula is this way. So again, let's consider event A and event B. These are two independent events. So let me just draw a line here too. So we have two independent events. I'm going to use set theory to just demonstrate the formula I just showed you. So say this is a sample space, and you have event A here and event B here. This is event A, and this second circle is event B. I'm going to use a different color to represent that. So this is event B with the red circle, event B, this is event A. So within the black circle, all possible outcomes associated with event A are present. Within the red circle, all possible events associated with event B are also present. Now, the probability of event A occurring is basically represented by the region within the circle. So this whole region here. And that represents all outcomes associated with A. So let's think of this region as representing the probability of event A occurring. Now, this region within the red circle, this whole region here, represents the probability of event B occurring. Now, if you think about it, if one says the probability of event A or B occurring is equal to probability of A plus the probability of B, what have you done? You've counted the probability of A occurring, and you've counted the probability of B occurring, but you've counted this region twice. Let me show you. When you counted the probability of A occurring, you counted this region, and you counted this region. So you counted this whole circle. When you counted the probability of B occurring, you counted this region, and this same region again. So you've counted it twice. And what the subtraction of the intersection does is it allows you to only count it once. So what you're pretty much saying is the probability of A, probability of B, minus this region, because what you're saying is I count this region and this, then I count this and this, but so I don't count it twice, I subtract it. That's what this equation means. So I'll just write it down again. Probability of A or B occurring for independent events is equal to the probability of A plus the probability of B minus the probability of A intersect B. Now I'm just going to demonstrate the formula we just learned using a more practical example. Instead of using events A and B, I'm going to define events A and B, but I'm just going to write them down. Write the formula again. The probability of event A or event B occurring when event A and B represent independent events is equal to the probability of event A occurring plus the probability of event B occurring minus the probability of both event A and B occurring. So let's say I have a die and I toss it once. So die, toss. You just have one die. And I define event A as getting an even number, and I define event B as getting a number that's less than 4, or less than or equal to 4. Let's put it that way. Now I'm going to draw the sample space again, the sample space of all possibilities. So I'm going to draw the following numbers. I'm just going to do 1, 2, 3, 4, 5, 6. Now this is sample space and it contains all possible outcomes from a die toss. You can get a 1, 2, 3, 4, 5, or 6. Now I'm going to break down these outcomes into events. Remember, an event is a collection of outcomes. Here, event A represents even numbers. So I'm going to compile all even numbers. So here we have even numbers 2, 4, and 6. The second event, event B, so that's event A in red. Event B is numbers less than or equal to 4. Which numbers are less than or equal to 4? 1, 2, 3, and 4 are all numbers that are less than or equal to 4. So I'm going to group them as another event, event B. Now, if you look at this sketch, what's the probability of event A? What's the probability of getting an even number? Well, it's the number of ways you can get an even number divided by the total number of outcomes. In how many ways can you get an even number? Well, how many even numbers are there? There's 1 here, 2, 3. So it's 3 even numbers, which are 2, 4, and 6. But how many outcomes are there in total? There are 6 possible outcomes. 1, 2, 3, 4, 5, and 6. So the probability of event A getting an even number is 3 over 6, which is equal to 1 over 2. Now let's also look at the probability of event B. The probability of event B is equal to the probability of getting a number less than or equal to 4. So in how many ways can you get a number less than or equal to 4? And what is that divided by the number of outcomes? Well, how many numbers are less than or equal to 4? And how many ways can you get a number that's less than or equal to 4? There are 4 ways. You can either get 1, 2, 3, or 4. So the answer here is 4, divided by total number of outcomes, which is 6. So that gives 4 over 6, which is 2 over 3. But I'm just going to stick to this 3 over 6 and 4 over 6. Okay, now I'm going to ask a question. What's the probability of getting A or B? What's the probability of event A or B? What's the probability of getting an even number or a number that's less than or equal to 4? So the probability of getting an even number, well, it's here, 3 over 6. Probability of getting a number that is less than or equal to 4 is here, 4 over 6. So probability of A or B, if you just said that is equal to the probability of A plus the probability of B, we'll be getting 3 over 6 plus 4 over 6, which is equal to 7 over 6. But you know that the probability of getting a number that is even or less than or equal to 4 is equal to, well, let's put it this way, the probability of getting a number that's even or less than or equal to 4. So we're looking out for numbers that are either even or less than or equal to 4. Now 1 is less than or equal to 4, 2 is less than or equal to 4, 3 is less than or equal to 4, 4 is less than or equal to 4, 5 is not, but 6 is even. So we count 1, 2, 3, 4, and 5. Probability of A or B is 5 divided by total number of outcomes, which is 6, which is 5 over 6. But here we use the formula P of A plus B of B, and we go 7 over 6. This formula is wrong. It's wrong. The correct formula is the following. Probability of A or B is equal to probability of A plus the probability of B minus the probability of A and B. Now, what is the probability of getting A and B? Now, here is a different case. Probability of getting a number that is less than or equal to 4 and also even. Now, which numbers are less than or equal to 4 and also even? 1 is less than or equal to 4, but it's not even. 2 is less than or equal to 4 and is even. 3 is less than or equal to 4, but is not even. 4 is less than or equal to 4 and it's even. So there are only two possible ways. So the probability of getting, let's put it this way, probability of A and B, probability of getting a number that is both even and less than or equal to 4 is given by the following fraction, 2 over 6, because there are two possible ways, divided by total number of outcomes, which is 6. So it's 2 over 6. And from this formula, probability of A or B is going to be equal to probability of A plus probability of B minus probability of A and B. Probability of A is 3 over 6, probability of B is 4 over 6, so 3 over 6 plus 4 over 6 minus probability of A and B, which is 2 over 6 here. And this gives 7 over 6 minus 2 over 6, which is equal to 5 over 6. Notice this 5 over 6 we got here by using the correct formula is the same result we got by just inspecting the sample space. And the probability of A or B equaling the sum of the probabilities was shown to be wrong, as you can see here. So just remember the formula. For two independent events, the probability of getting one or the other is equal to the sum of the probabilities minus the intersection of the probabilities of, if you have two events A and B that are independent, the probability of A or B is equal to probability of A plus probability of B minus probability of event A and B occurring. The probability of event A or event B occurring is equal to the probability of event A plus the probability of event B minus the probability of event A and B occurring. Is very important, which is why I'm repeating it again. In the last example, we had two events. The event that a number was, two events. The event that a number was even, and the other event was that the number was less than or equal to 4. Now, I'm saying this formula applies for independent events. Now, in most questions, you'll be told whether the events are independent or not. And if they're independent, all you have to do is just use this formula. But imagine you weren't told that the events were independent. How you solve this problem if you're told that you need to determine the probability of event A or B occurring, where this is event A and this is event B. Well, all you have to do is just a quick check. Remember, I told you that an event is independent of another if, for instance, event A is independent of event B if the probability of event A given that event B has occurred is equal to the probability of event A. So let's look at the sample space. Remember, it was a die toss and we had a number of possibilities. So I'll just write them again. 1, 2, 3, 4, 6, 5. I did that intentionally. So 1, 2, 3, 4, 5, and 6. So there are 6 possible outcomes. Now, what is the probability of A? What's the probability of the number being even? The probability of, I'll use a different color, of getting an even number, so the probability of event A is simply 3 over 6, because there are 3 ways of getting an even number out of 6 outcomes. what's the probability of event A given that event B has occurred? So what's the probability of event A given that event B has occurred? So what's the probability of getting an even number given that the number obtained is less than or equal to 4? So now we only have, given that the number obtained is less than or equal to 4 means that we only have 1, 2, 3, and 4 as a possible outcome. So given that event B has occurred means these are now the total number of outcomes. We only have 4 possible outcomes. So what are the number of ways of getting even numbers? Well, there are only 2 even numbers. So the probability of event A given that event B has occurred is equal to 2 over 4. Now, for events to be independent, the probability of event A given event B must be equal to the probability of event A. Here, the probability of event A is 3 over 6, which is what? 1 over 2. The probability of event A given event B has occurred is equal to 2 over 4, which is also equal to 1 over 2. As you can see, they are the same. So events A and B are independent. You don't really need to worry too much about this, but I'm just demonstrating this note on independence. But just make sure you know that this formula applies to independent events. And for mutually exclusive events, you know that this will be 0. So this will be the formula when you're dealing with mutually exclusive events. That's all you need to know.